And we're going to pick up with our next chapter here on gases. You send it full screen. Everything this chapter is basically this equation you see right here. I know it's, a little confusing, it's trying to mesh into the champagne bottle opening, but it's P is pressure, V is volume, and that's equal to N is the number of moles. That's sort of the new one that, maybe doesn't ring as obvious as P and V, and then T and R is a gas constant. But N is the number of moles is consistent throughout chemistry. It just doesn't, it isn't M for moles or something, it's N, but it's the number of moles. Okay, so first let's just talk a little bit about gases and potential ways you've already experienced this. So what this is showing is just, out in the middle of nowhere, when you're not in a city, you'll have these wells, right? And they dig down and they tap into some water that's underground, and you get the water out. If you see really old ones, they'll have hand pumps, but this one here is showing us some sort of electrical pump, whether it's a generator or you're on the grid, etc. All right, and so the way this works is basically by reducing the pressure inside. So before you turn the pump on, or like this is saying the pump's off, and it's the same thing when you drink a liquid out of a straw, right? You suck on the straw, that reduces the pressure. The pressure on the outside of the column or the straw is still the same, and that's just atmospheric pressure. And so that in effect is always pushing down on the water, but nothing is pushing down on the water on the inside now, and so the water draws, or the liquid, whatever it is, draws up. Okay, there's a few different units in here. We're basically going to stick to atmospheres and millimeters of mercury, but there are a few others. So what this is just showing is this is this typical value when you have a really good vacuum near zero, although no vacuum is 100%. You can get water up from about 10.3 meters, right? A meter is about 3 feet, so about 30 feet, something like that. One of the other ways you see pressure expressed is in pounds per square inch. And that's because what pressure is a force divided by an area. So a way to think about this is if you took a book and you put it on the palm of your hand, and you hit the book with your fist, with your other hand, you can feel the pressure from the book against your hand. All right, so if you use the same force, just tapping it with your fist, but if you took away a book and you put in a pencil, why is that pencil going to go jabbing through your hand? It's because the force was the same, but the area was reduced. So all of the force got put down to the point of the pin. Instead of the square, right, inches squared, instead of the size of the book, let's say the book was 12 by 12 or something. So the force was still the same, but the pressure was different because the area shrunk. And this is basically why if you've ever ice skated, when you see ruts in the ice, is because the person is skating on just a sharp, thin blade, right? When you step on ice, you don't see the same kind of mark. That's because the pressure of the weight of your body gets put out all over the entire shoe. But when you ice skate, it goes right down onto the edge of the ice skate. And so the pressure is much greater. Okay, so we want to think a little bit about the way gases move. And basically, gases move in every direction. They're bound by nothing. It's sort of like bumper cars, or if you've ever seen a demolition derby, where you have two cars or whatever colliding into each other, but they're limited by gravity to just two dimensions. Gases aren't, right? They can go in all three dimensions. All right, so they move and strike kind of like if you've ever played billiards, pool, the balls hit each other and go bouncing around, but that's limited by two dimensions, and then also there's kinetic, there's friction and whatnot that slows down the kinetic energy. The balls eventually slow down and stop. Gas molecules never stop. All right, so the pressure that a gas exerts by colliding with some surface, we can measure that. And again, that's that force per unit area. All right, so these differences in pressures are basically where weather comes from. And things always go from the higher pressure to the lower, right? So you blow up a balloon, and when you let go of it, it goes, flying, zigzagging all around the room. And the greater pressure that you pushed, blew into the balloon with your lungs, wants to equilibrate with the lower pressure outside the room. So if this down here, if there's something in the gas path, the gas will try to push it along as the gas flows. And this is basically the way a gun works. So the way a gun works is you have a cylinder, the bullet is in the gun. You have generally what's called a hammer. It's that, you see it in the revolver kind where it cocks back. It comes forward, it hits the back end of the bullet that has some gunpowder. That friction of metal on metal colliding causes a spark. The spark ignites the flammable gunpowder, and the reaction is a combustion one that takes a bunch of solid material, turns it into a gas, and then that gas pressure pushes the bullet forward out of the cylinder, right? Not really that high tech. All right, and so these differences in pressure, that's what gives us weather and different wind patterns. The higher up in the atmosphere you go, the lower the atmospheric pressure is around you. So just like when you jump off a cliff into the ocean or on a trampoline, gravity pulls you back down. Same thing with all the gas molecules on Earth. Gravity is always pulling them down, and they're bouncing around in three dimensions. And so as you go up in elevation, there's less and less of them, right? Because gravity is always pulling them down, but they're not a solid or a liquid, so they go in three dimensions. And as you move up in atmosphere, there's less and less gas molecules, so there's less and less pressure. You feel this when you go up and down, even in a car, if you go driving up and down a mountain. But I'd say in a plane, it's more dramatic. You notice that pop. And the reason for that, what we call popping, is what you see here. So this would be if you were going up in an airplane. So it's showing the normal pressure by the number of gas molecules. And, the blue ones are nitrogen, the red ones are oxygen. So you have this thin little lining. This is your eardrum, this thin piece of skin. And it's thin enough, and that's one of the reasons it gets damaged if you fall into water hard enough, and water can come in here and actually break the drum. But it's thin enough that given a pressure gradient, gas molecules can move through it. So you only feel this when you're, in a car or a plane. It's pretty tough I don't know that you can do this on your own, like hiking, and feel your ears pop while you're just walking. But what we see here is it's popping in the out direction. And I don't know, I can't tell the difference between the ear popping up or down, but you obviously know which way you're going. But this would be if you're taking off in a plane and then you get high enough and the pressure changes, and the popping is when a significant amount of these gas molecules go through at one time and you get some vibration in the eardrum. All right, so the result of a constant movement of gases molecules and their collisions with surfaces around them. That's basically what the pressure is. And this is coming up with that ideal gas law building up. So the pressure, or P, is related to several things. The number of gas molecules, so that's basically the number of moles. V, the volume of the container, and then average speed of the gas, which is a function of temperature. So this is really saying temperature. So this is basically our ideal gas law, P, V, and T, and then what's not mentioned here is the gas constant, but we'll see this coming up. All right, sometimes you see this on the news. If you watch the news and they mention the weather, they'll tell you whether the barometer, is falling. And they use these in chemistry labs, but they're pretty old-fashioned. I haven't seen any in a while. Everything's gone digital. This is sort of like a sundial or a rotary phone. It's an old technology. But they would have these in a chemistry lab where you have liquid mercury, and then you would have a yardstick next to this and a glass column, and you have a vacuum that's hooked up to this, and it would pull up the mercury. And 760 millimeters, if you're not, is about a yard. I forget exactly the exact number, but it works nicely before the world of electronics. Now we have electronic gauges that will measure it, but before this, you would have this set up to chemistry setup, and the mercury rising would tell you how good your vacuum was. And vacuums are important in a lot of chemical applications. So gravity's pulling it down, your vacuum's pulling it up, the atmospheric pressure or the lack of atmospheric pressure here and the atmospheric pressure on the outside push it up, and then how high it goes up is a function of how good this vacuum is or how few gas molecules are here on the top side. Okay, so there's several units, and which units you use just depend on what field you're in. So engineering and physics tend to use the pascals up here. Inches of mercury you see on the news, pounds per square inch. This sounds like engineering, right? In chemistry, we tend to use atmospheres, and then millimeters of mercury and torr are the same thing. So 1 to 76. It'd be worth noting or writing down, there'll be some conversion where you have to go back and forth between these in Chem 162 as well. All right, so here's our first little example. This one's going to be pretty easy. It's just changing units, right? So some bike tire, who cares what it is, 123 psi, we want to go to millimeters of mercury. So we know the unit we're in, we know the unit we're going. How are we going to get there? This one decided to go through atmospheres. If you wanted to, you could see them lined up and just take 14.7 psi and 760, since the common link here is atmospheres, but it's fine the way they set it up, right? Since, it's just a 1, and anything multiplied divided by 1 is still 1. Right, and so good classic dimensional analysis practice, units on the bottom, and your first conversion of the units they gave you, then the next unit on the bottom and your next conversion factor, your units cancel, and we get a value out that makes sense, right? And this was, about 10 atmospheres or something, and so we should get something about 10, right? So those are pretty easy. There'll be one of those on the test. That's sort of, the check mark of an easy problem, which we just went over the exam, and I pointed out some of the easy ones. We saw the barometer. There's also these things called manometers. It's essentially the same kind of thing, and you're looking at these liquid levels. And I thought on the next slide I was going to show a picture of it. You won't ever see one, unless you're going to be a chemistry major and go into grad school. They all use electronic things now. So it's just mentioning it in here for the the outside chance that a chem major's in the class. I'm not going to read all this to you, but it basically works the same way as the barometer did. It's just a little fancier setup. Okay, so we get to the ideal gas law, which is everything we do this chapter is some shortened or special unique version of this. So this was just what was on that last slide, right? That the pressure was related to the volume, the number of moles, and the temperature. So you can arrange it several different ways. This is the common way that it's said. PV equals nRT, and that was what was on the first intro slide. This is also a good thing to note for the next exam. This is the gas constant you want to use. So if you go look up, type into Google or, even look on Wikipedia, there's lots of different numbers for the gas constant because you can interconvert and use lots of different units, right? You could change liters potentially to gallons and atmospheres to pounds per square inch, and that would change this number. But this is the one that we're primarily going to use all chapter and, the whole semester. And it's also the common one that you'll use in Chem 162. Okay, then there are shortened versions of the ideal gas law where you just look at a couple of the features, and each one has a famous scientist's name after it. Again, you saw like on the last exam, it's not a history test, so I'm not going to ask you whose law is whatever, and you could just look it up anyway. But Boyle's law looks at the relationship of from the ideal gas law, that the pressure is inversely proportional to the volume. So basically all of these, let me go back one, is where PV equals nRT. If you rearrange it like this, PV over NT is equal to a constant. So if it's constant, then just like the dilution equation, M1 V1 is equal to M2 V2, P1 V1 N1 T1 would be equal to a constant. Thus, it would be equal to P2 V2 N2 T2. All right, then if anything is staying the same, you leave it out. So that's why our in the dilution equation, M1 V1 equal to M2 V2, there was no 4 variables. There was just the 2. So if the temperature is held constant, you leave that out of this expression. If it's not the number, if your number of moles and temperature are constant, then that drops out. And vice versa. Any of the 4 that are held constant don't need to be included. Okay. So again, right? This is saying if your number of moles and your temperature are held constant, then you don't need them in the equation. Then P times V equals constant. Then P1 V1 is equal to P2 V2. And the reason it's inversely proportional is because you're multiplying these two together. It equals a constant, then it must equal the same pressure and volume under different conditions. If you're multiplying them, if one value goes up, the other value has to go down compared to its partners on the other side. So, P1 V1, if P2 is higher, that must mean V2 is smaller. So here's this classic example, right? We use the measurement in here to relate to the pressure. So again, you would use, in a modern day, you would use some electronic device, not this. But we have this, this gas here, we measure the volume, that's our difference. And then you pour in more mercury that changes the pressure, and we see a change, right? But the important thing here is the number of moles of the gas hasn't changed, and the temperature hasn't changed. So this is a classic P1 V1 equals P2 V2. And throughout this text, you'll see where they like to plot things. We'll see this again. And that's directly, right? So pressure, volume. And high, one value is high, the other small, and then one value is getting high, the other small. So it has this type of interaction. But if you plot it down here inverse, so if you plot it that the pressure increases and then 1 over the volume, you get a straight line. Right? And if there is no pressure, there should be no volume. So this is going through the origin and has a y equals mx plus b, where b is 0 type of your straight line linear plot. Okay, so here just shows, this is just the data, I think, from that last slide, right? And in this instance, it worked out to a nice round number of 1400. And they just show you a few examples, right? Our volume's going down, and so the pressure must go up, because it always equals this constant. Right, and the guy who made this book, and it's rightfully so, I think, just loved the internal combustion engine. And this math is really easy here. Here's a weight that keeps the lid on it here, so it doesn't come off or whatever. Now this is a little more typical, right? Not a mercury in a manometer or something, but 1 atmosphere. You double the weight that's on there. Let's say double the pressure. So if this comes down, the pressure increases, the volume has to decrease. And here our math is real nice, right? 1 times 1 is 1. So if it's twice the pressure, then it must be half the volume, right? 0.5 times 2 is 1. All right, if you're scuba certified, you probably know plenty about this. And so there's sort of this rule of thumb about for every 10 meters you dive down, the pressure increases about 1 atmosphere. So if you're diving down, 20 meters, which is pretty far, but 60 feet-ish, something like that, it's 1 atmosphere at sea level. So the first 10 meters is an atmosphere, then the next is yet another. So about 30 atmospheres. All right. So the problems on the exam will be similar like this. These ones are good. Let's take a look at a cylinder with movable piston has a volume of 7.25 liters. It's at 4.52 atmospheres. What's the volume at 1.21 atmospheres? So it's inversely related, right? This went down the atmospheres, and so we're expecting the volume to go up, right? As one goes up, the other goes down. So this went down, we would expect it to go up. So it looks, just off, let's call this, round this off to just 4 and this to 1. So that rounds them both down. It decreased by about 4. Let's call this 7 liters. So it's going to increase by 4. I expect the answer to be close to 28 liters, something like that. All right, so there's our P1, V1, P2, T2. As long as the units are all the same, they'll cancel. So, right, they're both in atmosphere, so they'll cancel. That means our V2 is going to be in liters. We know P1, V1 equals P2, T2. So rearrange it and solve for the missing thing. That's V2. We do that by dividing both sides by P, and then just plug in the values. And again, I was ballpark expecting something near 28 liters. And you kind of saw on the last test where when it's multiple choice, especially, you can just eliminate answers that are ridiculous. So, we know it's going to be bigger. So anything that was lower than 7.2, you could get rid of. And then we knew it was going to be about 4. So something that was 10, 20, 30 liters bigger, you could eliminate those. The units cancel. This is about the only way to mess up on these, is forgetting to have your pressures in the same units. And since all you need to do is have your pressures in the same units, it doesn't matter what your units are for pressure. Go to the next. I don't know why. There we go. And again, it did a pretty good example here of what I was talking about, where you could already kind of make a prediction of what to expect on the ballpark volume. Charles law. So each one of these, again, is named after a famous scientist. It's not a history class. You don't need to know it. If you're a chem major, you want to make note of these, but for everyone else, it's not that critical. And you can see here what we're going to do is just take the ideal gas law and have things held constant and look at how the other things still left in the equation change. So volume is directly proportional, not inversely like last time. Constant P, so our pressure is not changing. The amount of the gas isn't changing. So this is where V versus T gives us the straight line, not the curved one like we saw before. So as T increases, V increases. And this is why we need Kelvin. Your temperature has to be in Kelvin, because with Celsius and or Fahrenheit, you can have a negative value, and that doesn't make any sense. So this is the Y equals mx plus B type of thing. So, right, it was PV over N and T. The P and the N were held still, so all we're looking at is V1 T1 to V2 T2. In the classic way this is shown, if we had an in-class, if we had an in-class format here, and or like the way I usually do it is I go get liquid nitrogen. It's much more interesting than just ice water. So you can blow up a balloon, and then you pour a bucket of liquid nitrogen, you dunk the balloon in there, and it shrivels up to almost nothing. But you can do this one at home. It's just the temperature gradient. The difference is much bigger for liquid nitrogen, which I don't have liquid nitrogen at home. So, but the idea here is that you blow up the balloon, you tie it in a knot. So the volume, it can change. But since it's rubber, the pressure doesn't change, right? It stays at roughly, the outside pressure is 1 atmosphere. That doesn't change, and then the rubber is flexible. So the gas can't escape, the number of moles stay the same, and then just the volume with the temperature. All right, and then here they take some hot water and you see it expand, and this is basically the way a hot air balloon works. All right, so the number of gas molecules in there is the same. We change the temperature and we see the volume change with it. Okay, so this is one of the ways you can rationalize what absolute zero is they take a bunch of gases at different volumes and they track them at different temperatures, and then you interpolate, and all these come back and meet at the same temperature, right? Because a gas, if if you were at absolute zero, then, obviously it wouldn't be a gas, it would be a solid, but it should have absolutely no motion, right? Even no vibrating, right? So as things move slower and slower as gases, then they become a liquid. Then they move slower and slower as a liquid, then they become a solid. And so all of these are plotted where they're still gases, but the plots all go back to the same point of absolute zero, right? And this is one of the reasons there's other experiments that physicists get all into that gives us this 273.15. Okay, so an example. Temperature inside the balloon's raised 25 to 250. If the volume of the cold air was 10 liters, what's the volume of the hot air? All right, so initially when you look at this, you might think, okay, 25 to 250, that's times 10. This is 10 liters, so it should be 100 liters. But the trick is that temperature is not in Celsius. It's in Celsius, and it needs to be in Kelvin. So when you go The math is all still the same as before, right? Directly related, rearrange and solve for the thing we want. The temperature needs to be in the same units and cancel, but the temperature needs to be in Kelvin. And so now when you look at the new change, 298 to 523, it's not the same as 25 to 250. It's not a 10-fold increase anymore, right? 298 to 523 isn't even twice as much. So it should be less than twice as much. So if the volume was 10 liters, then it should be what, like 18 liters or something, right? Because 2 times 298 would be 600. It's less than 600. So some number that's lower than 20. Units cancel. We're in the same units that we left in there, liters. And so 17.5, that does make sense. Not the 100 liters that you would have predicted if you left it in Celsius. Avogadro is, we saw his name before with Avogadro's number. He has a law named after him. Again, broken record player. It's not a history class. You don't need to know the name. That's not going to be on the test. You didn't see that any name stuff on the last test. Since he's where a mole comes from, obviously this one is going to be dealing with the number of moles that N. So this one's saying, all right, if V is constant, V equals a constant times the number of moles. Now we're keeping P and T constant. This is that direct relationship. So it should go through the origin at 0, right? If you have no gas molecules, how can there be a volume? And then as you have more gas molecules, you should have more volume, right? And you've done this before if you've ever blown up a balloon. So when you go to blow up a balloon, you blow one breath in, that shoves, whatever the number of moles of your lung capacity is, and then the next breath shoves in the same number of gas molecules. Now, obviously, as you keep doing that, the pressure builds up in your lungs. You can't keep putting in that same number of gas molecules. But if it was some, mechanical hydraulic thing, it wouldn't, again, it doesn't matter which gas, you would just have a straight linear plot as the volume would increase indefinitely as you added more gas molecules. So that's V, right? It was PV over NT. T isn't changing, P isn't changing. So V1 over N, N1 equals V2 over N2. So here's a sample like that. All right, we've got 0.225 moles. It's got a volume of 4.65. How many moles must be added to get to 6.48? So it's not quite double, right? If you're just guessing at this, let's call that 4.5. Times 2 would be 9. This isn't 9. So it looks like, 2/3 or 3/4 or something. So I'm going to guess 0.31 moles total. You'd have to add 0.11 moles. But let's set it up. Right, our volume, we rearrange and solve for the thing that is alone, and they gave us moles, so that's the unit that we'll get out, which obviously needs to be moles. The only difference here is it's asking the moles added, so we have to do one little manipulation. The value on your calculator initially won't be the right answer that is actually asking for. All right, our volumes are both in liters, so that's going to cancel. I was pretty close, right? The new total volume is 0.31. The only difference is here is it asked for how many moles must be added. So we wanted to go from 0.225 up to 0.314, which means we needed to add whatever the difference between those two were. So 0.089. And then sort of, like I guessed at it, directly related, we knew the number was going to increase. We knew it wasn't going to double. So somewhere in between doubling, so like 1.5 times bigger, which when something's 1.5 times bigger and it's a 2, that means it's just a 3. And then 2 minus 3 is, this number is close to 0.1. So Number seems like it makes sense. All right, this is that same slide just put at the end where now you kind of have seen each one of those put in here. And you kind of see now a good way to write this, the equation is like you see on the left, and then put a 1 next to these, have it equal to R, and then equal to, all the conditions with a 2 next to it. So P1, V1, N1, T1 is equal to P2, V2, N2, T2. So then ones that just use the full ideal gas law are all these solve for the unknown, right? So the R is a constant. There's 4 variables in the equation, so you're just solving for the missing variable. In this one, how many moles of gas are in a basketball with a total of 24.3 psi, volume 3.24, and at 25 degrees? So the first thing I noticed before we tackle this, psi is not going to work for the gas constant that we use, and neither is Celsius. So they gave us PV and T. The problem is they're in the wrong units. So first thing you're going to want to do is switch those to the right units. And then we know the ideal gas law will get us to what we want. We need to rearrange it to get the thing that we want by itself. All right, get the pressure into the right units. And these little underlined here scores are saying, right, you've got 3 sig figs in the numbers. So our answer that we're, keep as many digits on the calculator, but we're going to want an answer with 3 sig figs. Right, the psi units cancel. Right, we want to move to Celsius, to Kelvin from Celsius, and then it's just plug and chug and solve for the unknown. Now, as you get more and more numbers in here, and this one wasn't a change from one condition to the next, then these get harder to predict. All of our units cancel. This little check here that it's suggesting, we haven't gotten to why this would make sense yet. So, but if you, after doing the whole chapter, if you went back and did this problem, then this check will make more sense then. Okay, standard conditions. What are standard conditions? So it turns out that the majority of humans on Earth live near the ocean. And the ocean is sea level, and the pressure at sea level is 1 atmosphere. So almost everybody that's been doing science all these, whatever you want to call it, hundreds to thousands of years, has lived at sea level and done all of the experiments and everything they've ever done at 1 atmosphere. Okay, then if you can just get your hands on some ice, which if you live somewhere that's cold enough in the winter, you can just go get snow from outside. Then you can run chemical experiments at 0 degrees. And then nowadays we have ice machines. So these conditions of sea level, 1 atmosphere, and ice, or 273 Kelvin, is called standard temperature and pressure. Right. What happened there? The format changed. Anyway, so let's do a little problem here. A gas occupies 10.1 liters, 44.1 psi, and 27 degrees. What volume will it occupy at standard conditions? So now we're going to use the ideal gas law to find the number of moles, and then change the conditions and predict what volume it will be at those STP conditions. So sort of 2 problems in one, and it'll make sense why in a minute when we get to it. And there's sort of 2 ways to do this. You can do the whole P1, V1, N1, T1 to P2, V2, N2, T2 type of thing. But here, let's first do this, right? We have to find that N to do it. And then we know the N stayed the same. And then we can apply all the second conditions. And we know the gas constant never changes. Okay, so let's first plug in all the stuff they gave us. It's got to be in the right units, and we can find N. And then in the second conditions, now that we know N, we can apply that STP and find the V. All right, so get out of PSI and get to atmospheres. This one worked out nicely. It's right at 3. 27 plus 273 is 300, so kind of nice round numbers. 10 liters, right? Nice round number. 1.219 moles at these, unique, whatever, random conditions, right? What about at the standard conditions? So now we take the moles that they gave us, 1 atmosphere and 273, and we get 27.3 liters. Okay, so if you take this same equation in here, right, 1 atmosphere, 273, and you didn't put 1.2, you just put 1 mole, it turns out that 1 mole at STP is exactly 22.4 liters. So this becomes a new conversion factor. Like there's 12 inches in a foot or 24 hours in a day, and 1 mole at STP is equal to 22.4. This problem just walks you through and shows you from some random conditions then at a STP. And this isn't exactly 1 mole, but it's pretty close, right? It's bigger, and so the volume would go down. And so if you put in a 1 here instead of 1.219, you get 1 equals 22.4. And this is what's called molar volume because it's 1 mole. So this is just what I was saying there. If you solve the ideal gas equation, the ideal gas law at STP, and you just put in 1 mole, it always equals this 22.4. So what they noticed and why there is an ideal gas law is that it doesn't matter what gas is in there, which gas you use, it doesn't matter. So in Chem 162, the first couple chapters are on liquids and solids, where there is no ideal liquid law, there is no ideal solid law, because they all behave differently, but the gases do not. So you can just call it the molar volume. And when you're at STP, you know what the volume is for 1 mole, regardless of what the gas is. All right, what this slide is trying to show is that if you're at STP and you have these tanks, it wouldn't matter what gas is in the tanks. If you had a balloon that would only go to this volume, and you turn the valve, the 22.4 liters is going to be 1 mole regardless of what gas is in there. And the reason for this is gases are moving so fast and the density is so low that the volume of the individual gas molecule is irrelevant to the greater empty space between the molecules, which isn't true for liquids and solids. Okay, density we already learned about, right? That's mass divided by volume. So we treat the gases the same with the ideal gas law, but the molar masses of the gas aren't the same. So there'll be different densities of gases. The density ratio is the ratio, density is the mass to ratio. The density of a gas is in grams per liter. So if you remember from last chapters, our densities were in grams per milliliter, right? And that's because liquids and solids are much more dense. This is grams per liter. So that's telling you that ballpark gases are about 1,000 times less dense than typically, like water, but solids, liquids and solids, all. Okay, so the mass and then the molar mass gets you to the number of moles, right? And you can rearrange that. Density is mass in grams over liters. we know that PV equals nRT. The number of moles is the mass divided by the molar mass. That's just substituting in, right, these equations from above. So the mass divided by the volume gives us the density, and we know the pressure times the molar mass divided by RT gives us the density as well. So the density is then directly proportional to the molar mass, right? All right, so let's do one. Knowing and combining these different equations and relationships. This one, calculate the density of N2. And this is basically, right, you've been to some party somewhere or something, and you've seen how helium balloons float, just like when you're in water or in a pool, the ocean, you blow a bubble and it goes up, the gas is less dense. Helium is less dense than nitrogen, and so the helium balloon floats just like the way something floats in water. It's less dense, right? You throw a rock or a penny into a fountain, the things that are more dense sink to the bottom. All right, so our units aren't right here for what we want. We want to get to the density. We know we need the pressure, the molar mass, temperature, gas constant. That'll get us to the density. We need to get things in the right units. We need the molar mass of nitrogen, so 14 times 2 because it's N2. We got this equation from the last one, right? Density is mass divided by volume, so we have the equations for those. And then it's just kind of a plug and chug. All right, our pressure is basically 1 atmosphere, right? 0.993 is basically 1. And then we're at this elevated temperature for some reason, 125 degrees Celsius, fine, whatever, add it to 273. And then we just plug and chug along here, right? Our moles will cancel and we can get 2 grams per liter. And so these densities are known for different temperatures, but they're usually reported for more common temperatures like room temperature, STP. The density of N2 is 1.25 grams per liter at STP. And this is lower, which it should be. It's hotter, right? And this is the way a hot air balloon works. So, you know, I mean, most of the time you're in a hot air balloon, it's probably not 0 degrees. That would be, you know, 32 Fahrenheit. But they have a blowtorch that's connected to the hot air balloon, and they just pull the torch. The torch gives off a great amount of heat. It traps, the balloon traps the hot air inside the balloon. And so the density of the air, just normal air, not any special air, but normal air, is then lower. And so it becomes lighter than normal air. And so it'll float. And if you open up a cooler that doesn't have ice, but just water, you know, all the ice is melted, you'll see this with different canned drinks. And, you know, like Gatorade has different sugars and things and ions that are heavier than water, and so it sinks to the bottom. You got to take the weight of the can or bottle into consideration, but you'll see some float and some sink, and it's the same idea here with the hot air balloon. All right, one of the methods chemists use to determine the molar mass of an unknown substance is to heat a weighed sample until it becomes a gas, measure the temperature, pressure, and volume, and use the ideal gas law. This is an old way of doing this. I've never done this, but it is possible to figure out the molar mass of things. Now we have this, again, this is like a sundial versus a digital clock. We have much more fancy electronic ways, but this is one of the ways they used to do this before computers. The molar mass is the grams divided by the moles. And so this is just going to be one of these problems. Calculate the molar mass of a gas with a mass of 0.311 grams that has a volume of 0.225 liters, tells you the temperature and the pressure. So there's everything that we were given. We know what we're looking for. We've got our ideal gas law. We want to get to N, and then once the information given from the number of moles, we can come up with the molar mass. We got to get everything in the right units so it'll convert, right? Rearrange the ideal gas law to get the thing we were missing, N. And then given the number of moles, they told us the mass, right? 0.311. So all this is it's the same problem before, but it's doing this extra little math to find what they asked us for. All right, as typical you see in here, we need the right units. So we need to be in Kelvin and atmosphere. Then it's a pretty straightforward plug and chug from the things given, right? The liters, we change to atmospheres, change to Kelvin, gas constant never changes. Now we know the number of moles. Units all cancel. The grams that they gave us, we divide that by the number of moles, and we get 3.19, pretty close to 32 grams per mole, which is likely oxygen, because oxygen is 16, but it comes as O2. 2 times 16 is 32. So for this one, like the last one said, you could heat it up and then, into the gas phase and figure it out. Most gases, things that are normally standard temperature pressure gases, are things like helium and neon and carbon dioxide, etc. But things that are gases have lower molecular weight. So if you got some huge number for this, that would be really strange, right? And the temperature here was 55 degrees. So this is pretty close to atmospheric conditions. And so we're expecting a low molar mass. Okay, for example, the air we breathe is a mixture, right? Gases mix together, nothing stops them from mixing. We can use the ideal gas law regardless of the gas. So the ideal gas law works when we're just talking about the air that we all breathe, because it works for any gas. So what this means is that if you know information about each portion of the gas mixture, you can just add them together. So if you want to consider them all the same, or you have them individually and just add them together, it doesn't matter, because all the gases are at the same temperature, so they have the same kinetic energy. They all completely fill the container. And therefore, we can just treat the mixture as one big gas. So if you could somehow measure one of them, that would be called part of it, right? And the pressure associated with the one gas would be called the partial pressure. And so if you can calculate just part of it, that would then be a fraction of the total. And then if you know all the parts, you can just sum up all the parts to get to the total. Again, not a history class. There's another name here, Dalton. If you're a hardcore science major and into these, or you're going to be on Jeopardy, or you're a Chem major, you should know these. But you saw in the last exam, there's no points for history for the history lesson. So this is called Dalton's law of partial pressure. Should have probably been the title of the slide, but anyway. All right, so for example, the air that we all breathe is a mixture, and there's many more gases, but their percent or contribution are really low. It's basically 78, 21, and 1, right? And carbon dioxide is, this is a pretty small percent. There are other gases, but this is predominantly what makes up the air we breathe. Okay, so let's say you have two gases, call them A and B. The pressure, just rearranging the ideal gas law for A, is then equal to Na, R, T, and V, right? And the pressure of B is moles of B, R, and T over V. So the only thing that's changing here is the number of moles, right? If, imagine you had two gases in a balloon. If they're in the balloon, they're at the same temperature, they're in the same volume of the balloon, the gas constant certainly doesn't change. And so really you can do this two different ways. You can solve for both P and V as written above, or you can find a way, if you have a possible way, add the moles of A and B together and then just insert them, since you're multiplying both of these by RT divided by V. So it just depends on what you're given in the problem. Okay, another example here. This one's giving us helium, neon, and then what the total is. There's our V and T. It wants the mass of argon, so it looks like we've got three gases, and we're missing the third. We know what the total is. So from the total, we can find the pressure of the missing gas, and then we know the volume and temperature, and so we can back calculate to the moles, and from the moles get to the actual mass. All right, we know ideal gas law and Dalton's. We're going to use each one of those. So first, we knew what the total was. The leftover gas pressure must be subtracting the two that we knew about from the total, gives us the third, the argon that we're looking for. For the ideal gas law, we don't want millimeters of mercury, so let's change out of that. It gave us the temperature, make sure that's in Kelvin, 298. Then we're just plugging in that P, solving for N. Units cancel. And then go to the periodic table and grab the mass of argon. So you can see here, this is combining, right? This was a question the other day. You can't forget everything that we did before on the previous exam, but there won't be specific questions like the previous one, right? We're not balancing anything, but you can't forget molar mass, what that is, or what density is. We'll still go on to use things. Here's another example, sample problem. Find the pressure of neon in a mixture with a total pressure of 3.9 atmospheres. Gives us the volume, temperature, and the moles of xenon. So it looks like we've got two gases in there. We know the total pressure, and we know the moles of one of the gases. So we can find the pressure of the missing one, right? They gave us the moles of the xenon. We can use that since VT and R don't change. We'll get to the pressure of the xenon, then we know the total and subtract the xenon, and we'll get to the pressure of the neon. So again, using the same two equations, but now the ideal gas law first, and then Dalton's second. As usual, things need to be in the right units. So this one, they gave it to us in atmospheres, that's good. The moles, obviously, so our liters and moles and Kelvin cancel. Pretty close to 1 atmosphere. It said it was 3.9, so a little bit of rounding here on your calculator, right? It didn't keep all the units and already rounded it off, but it's about 1 atmosphere. So 1 from 3.9 is about 2.9. And the reason it did 2 is because, right, 2 sig figs, 2 sig figs, 2 sig figs. So in theory, your answer should have 2 sig figs. A mole fraction is like it sounds, right? A fraction is one number divided by the other. So a mole fraction is a mole of whatever it is you're interested in divided by the total. And we saw here that the pressure is related to the number of moles. So the pressure of a gas is going to reflect the number of molecules to the total. So the P of the gas is the same as the P over the P total is the same as the number of moles of the gas over the total number of moles. So the symbol for mole fraction is this italicized X. And right, this is just whenever someone asks you how you did on a test, you report the percent, which is just the fraction multiplied by 100. So you're familiar with this, but what you're used to doing is the number of problems you got right over the total. So if we take this mole fraction and you multiply it by the total, you'll get the pressure of that individual gas, whatever it is. Oops, animation there. All right, so most humans, our bodies are adapted to breathe oxygen at a partial pressure of 0.21. And that's because the percent of oxygen, now it depends on how you do the percent, whether you do it by mole or by weight, but nitrogen and the majority of the other component is oxygen and nitrogen have almost the same mass. So their percents are pretty close no matter how you line it up. But almost everybody on Earth lives at or near sea level. So our bodies are set up to breathe partial pressures that have 0.21 atmospheres, because that's 20% of the total, of one atmosphere. So partial pressures of O2 that are lower lead to problems, right? Hypo is when you have less than you needed, and hyper is when you have more than you need. For whatever it is. So, hypothermia is when you don't have enough heat, and hyperthermia is when you have problems because of excess heat. So same thing here with oxygen. All right, so as you go up in elevation, say here Mount Everest, the total of the air pressure is reduced to about 0.31 atmospheres. And that means that the pressure of the O2 is that same 0.21 mole fraction times the total 0.31. So 0.311 times 0.211 means that the pressure of the O2 is 0.065. And this is why people have problems when they're up there, right? You need 0.1 before you start to have problems. And this is, 60%, 65% of that. All right, so then the flip side of that, it's also possible to have too much, right? And so that pressure turns out that it's 1.4 atmospheres. And this leads to, biological problems. We're not set up to operate that way. Then if you're a scuba diver, you kind of probably already know these things, but it's possible to have too much N2. And it has this nitrogen narcosis name. So people that do the deep sea diving, their pressures for these, it increases dramatically depending, how far you go down. Remember, it was like 10 meters was an atmosphere. So at a depth of 55, the partial pressure gets to this 1.4 where you run into problems. So if you're going well below, and you don't want to run at that level. So if you're going below, say 50, they use different gases. They use a mixture of helium and oxygen, because helium has no effect, right? Inert gases don't do anything, right? You've opened up a kid's balloon and taken in a breath, and it's humorous because it changes the volume or the pitch and the tone of your voice. But it doesn't react. You don't choke and die, right? It's non-reactive. Nitrogen's non-reactive too, right? And this is called Helox. But it's done at a lower percentage of O2 than in air, because when it's pressurized below that 50 meters, then you get the proper partial pressure of O2, below 1.4 and above 0.2 that humans are designed to breathe at. So here's, what we're all conditioned and used to breathing at, and then here, 30 meters down, so 1 atmosphere for each, so you're getting around 40 meters, and each partial pressure increases by the same ratio. So let's do one of these. Find the mole fractions and partial pressures in a 12.5 liter tank. We got 24.2 grams of helium, right? Grams don't do us any good. We want to get to moles. Same thing with the oxygen. So step 1 is to get out of the masses and get into the moles, and then the mole fractions are how we'll get to the individual pressures from the total pressure, and we can get the total pressure from the ideal gas law. Right, so masses to moles. With both moles, we'll know the fraction. Using the ideal gas law, we can get to the total. Then we take the fraction to the total and get the individuals. All right, so get out of grams and into moles. Grams cancel, right? So now we know the moles of the helium and the oxygen. The mole fraction is the thing of interest over the total. So it looks like it's, 98% ballpark helium, 2% oxygen. Now that we know the number of moles, plug it in to the ideal gas law given the temperature and the volume, and it's 12 atmospheres. And then to go back and take the mole fraction, so what's 98 of 12 and what's 2% of 12, right? And this is 2.64, so above the 0.2 that we're used to, but below that 1.5. So this would be an example of that tank that is good for deep sea divers to avoid those problems. Let me do a little time check. It's a few minutes early, but I feel like we covered a lot of stuff. It was kind of really only the ideal gas law and then unique situations of it, and then the partial pressures, but it's still a lot of sample problems and a lot of material for one day. So I'm going to stop there, and I'll hang around for any questions, comments, thoughts, feelings, etc. I'll post it and whatnot on La Lima as usual, but feel free to, what's today, Wednesday? We don't have class on Monday, right? Monday's a holiday. So kind of good to cover a lot of stuff as you actually have a holiday, and we won't get back to this for a while. So I hit the unmute. So if you want to questions, comments, thoughts, feelings, hang out. If not, I'll see you next week.
I have plenty.
All right, Nick.
Let's start with the density side first. If you can walk me through how like that happened again.
This one.
Yes, and then there's an example not that far from it.
Hold on, it looks screwy on my screen. Let me get back to it. Here we go. Yeah, so right, the density is mass divided by volume,
Yes.
right? And so if all you have is a gas, then the density of the gas would be the mass divided by whatever volume it is.
Okay. So it's
Okay.
just like that specific molecule or atom that,
Yeah.
okay.
Yeah, and then the ideal gas law has the number of moles in it. And the ideal gas law has volume in it. So you can mix the density, which is mass and volume, and the ideal gas law, which is PV equals nRT.
Okay, so since you have the density, you can substitute the number of mole, okay, because it says mass and molar mass. And the cancel, okay.
I usually don't put one of these on the test. I think it's a little much, but it is kind of
Yeah, because that was the next question.
yeah, well, I mean, there's plenty of examples of it, but I'm not that big a fan of these, but I like this one where we walk through it because you get down here to grams per liter, and it shows you how we did grams per milliliter, and the numbers, right, like the density of water is 1. So the reason it's in grams per liter, so you get a number that's comparable, right? It's kind of close to 1. And then here, this shows you, like, this one was at 125 degrees. So again, this is exactly how a hot air balloon works, is all you're doing is just making the gas less dense, right? Hot air balloons don't actually have a different gas in them like a helium blimp. It just has gas that's hot. And so it's expanded and it's taking up a bigger volume. And so the density is lower.
Okay, so. And next question is, so the main things, the main units we're gonna use like for pressure is gonna be ATM, correct? For like the class?
Yeah, yeah. You see atmospheres here in the gas constant. So in general on the test, I'll put 1 or 2 in where you change between millimeters of mercury and atmospheres. You saw it a lot in here because they want to hammer it home. But like
Yeah,
on our test, I'm going to, like, each problem tries to, introduce and emphasize a new equation or something and not have to make you do every possible unit, conversion in each problem, right?
okay,
To save time, but like, so there won't be one of, like, the test isn't long enough to have one of every single one of these example problems in there. So it'll probably be like one of every 3 we've done is what you'll see on the test from this chapter.
okay. And the gas constant, that's gonna be R.
Yeah,
Uh, what is the at AT,
yeah. Atmospheres times liters divided by moles times Kelvin.
they really decided to make this one complicated.
So
And, okay, I think I understand the density one. And then the partial pressures, and from then on was, that was just lost.
okay. Just pulling up. I'm waiting for the internet. I'm pulling up one thing. So let me change. If you go to Wikipedia, here's all the different gas constant units depending on what you're doing. So this one's pretty close because a bar is close to an atmosphere. But here's the one. Get that out of the way. Here's the one that we use. Right, this one. Oops. And we don't need to carry out this many digits, but it just changes depending on what other units you're changing. But notice the one thing that never changes is moles, right?
Okay,
Because it's a gas. But depending on if you're doing pounds per square foot or square inches or these pascals, and then some of the other energy ones, in Chem 162 we'll use this one, but that's for energy and stuff. Okay.
joules per Kelvin.
Yeah. Now let's go
Oh,
back.
yeah, the partial fractions portion was definitely confusing.
So since, right, like the air we breathe is a mixture, but when you use the ideal gas law, it doesn't matter what gas it is. And since if it doesn't matter what gas it is, then a mixture of gases behaves the same as a pure gas. And so what that means is just you see down here as the total of the gases behaves the same as if you knew information about the individual ones.
Okay.
So it would, the pressure of a gas is measured in units of atmospheres, just like money is like it doesn't matter how you get to a dollar, whether it's 10 dimes or 250 pieces or 4 quarters, right? So it doesn't matter whether we know what A and B are or we don't. Their individual pressures, if you wanted to, per molecule will eventually add up to the total that you experience because the gases behave the same regardless of which gas it is. And so the reason for this is only when you have some way to know and measure the different amounts. And like,
Can
what,
you walk me through how this step this problem,
so things, hold on, I gotta get this thing to move. It was blocking it for me. There. It's still in the way, huh? Like the bar. Oh, there.
yeah, cuz I have no idea where you found all these numbers in the screen.
So these ones here given. So this is just an error in like this example. Didn't put it up in the purple,
Okay,
right? Like you didn't know this information. So it's really start the problem from here.
okay, so would
Not
you
not from
start?
here. From this, you have no idea what to do. From here now, how do you solve the problem?
So I would just change all the units pressure for helium to atmosphere.
Well,
Same with
so sure, but you can also you don't need the atmospheres just yet. But what this is saying is you have here's helium and neon, and there's your total. The
Mhm.
helium and the neon obviously don't add up to the total, so there's some argon in there that we don't know,
Okay,
right? So from the total, we subtract the things we do know, and what's left over is the last gas,
yes,
right? So once we have that gas pressure, we know the volume and the temperature, we can use the ideal gas law to get to the number of moles. And then we know the molar mass, we can get to the mass of the argon that's there.
okay, so whenever you're looking for just mass, just think about the molar mass.
Yeah, to find mass, you have to know the number of moles.
What, and on that note, when you're looking for that mass, don't you have to like that NAR right before the mass of argon? Do you have to find, do you have to divide that by 22.4 somewhere along the line?
No, because like here it's saying, you're in this volume and you're at this temperature. It told you these conditions.
Okay,
So from this V and T and the pressure we find, the difference from the total, then we get to the number of moles.
okay, so you're just isolating, okay.
So this problem it's a little tricky because here's Dalton's and it's ideal gas law, then it's the molar mass from last chapter. So this is sort of this is kind of two problems in one, I think, to a test question. It's a little bit of or it'd be like one of the harder ones that you would leave to do last because it's just going to take a lot of manipulation. Whereas the earlier problems just did the ideal gas law part here, right? And then the molar mass we already did last test and last chapter, but you'll continue to do the rest of the semester and in Chem 162 as well.
Okay, I think I understand this one. So how about the one where You had to start with the ideal gas law, and then you had to do the Dalton's law afterwards, or was that it?
Yeah, that's this one, the next one.
Oh, I thought there was one where it was flipped.
Yeah,
Uh,
it is. This is ideal gas law first and then Dalton's second. So it just depends on what information they gave you. Like where you can start from.
okay.
So this one, it's saying find the partial pressure. Well, if you're finding the partial pressure, that must mean that the Dalton's is the last step.
Okay.
All right, and then here, and then it tells you the total pressure
It's
and
3.9.
yeah, and volume and temperature. And now it's telling you you got moles of Ze is xenon and Ne is neon. So we've got these two gases and we know how much of one and we don't know how much of the other.
Okay, so you do PV
So from this
equals.
one, yeah, we put in, take the total pressure and we can find, there's sort of two ways to solve this one. You could get the total, you could do the difference between the moles, or you can use the ideal gas law and get the individual pressure. And that's what they chose to do here. So from the moles, we know the R and the T and V, and we can find that bit of pressure and then subtract it from the total to get the pressure of the neon, which is what it asked for.
Uh,
You could have also found the total moles, subtracted the moles of the xenon, and then found the pressure. But this way is a little faster, I think.
okay. So as long as you have the, okay, that's the missing part that I needed. And mole fractions. Is
Yeah.
it similar to the Dalton's law or?
Well, so it just introduces the two because the mole fraction is just your percent, like the percent you got on a test.
Oh,
It's just a thing of interest, whatever you're interested in over the total. But it turns out when you look at it as the number of moles, that the mole fraction of uh, for gases, when you multiply it times the total pressure, you get the individual pressures because the pressures are directly related to the number of moles. You know, like, so let's say you always get 78% on an exam. Well, then you would just times the number of problems, which would be P total times 0.78. And that would tell you how many problems you would get right on every exam.
okay. Yeah,
So
I thought it would be 0.78 over 1 to get the percent.
sure. But so the mole fraction of the air we breathe is always 0.78 and 0.21. So the individual partial pressures just go up or down depending on what the total is. And so at sea level, it's 1 atmosphere, but as you go up, the total drops and the individual ones drop at the same ratio. The mole fraction stays the same regardless of whether you're at sea level or on top of Mount Everest. It's only the total changes. But when you multiply that by the mole fraction, you get the individual pressures.
Okay. Can can you play that example?
Well, you see it right here. So this is what it's saying, right? So when people go diving, they take a scuba tank and all they do is compress normal sea level air and they go up to 4 atmospheres. So
Yeah,
0.78
multiple of
times
4.
4 is 3.12. 0.21 times 4 is 0.84.
Okay, this, okay.
Yeah. So I don't like at you know at Mount Everest, the total is lower. It's 0.31. So 0.311 times 0.21 is 0.065. So here's where the P total is smaller, but we still multiply it by the same mole fraction. And then here's where P total is larger than what we're used to, but you still multiply it by the same fraction, and then you'll get the pressure of that contributing gas, whatever it is, nitrogen or oxygen.
Okay. Okay, I think I got this. This one makes more sense now.
Good. Okay.
And where did we just leave off?
We
I
stopped
don't know.
here collecting gases, because that's kind of a lab thing, and I don't know, I feel like we covered enough. So
Okay.
we'll pick up here Wednesday, since Monday's a holiday, and our next exam isn't for, like a month or something. So
Oh, another question. For volume for this class, what will we be using? Just grams per liter?
yeah, almost always liters, because that's what's in the ideal gas law that we use.
Wait, is it liters or?
Liters, yeah.
Okay.
Right, here's the ideal gas law that we'll use all chapter long, and liters is in there. So you want your answer to be in liters. That's the way to go, because it'll cancel out for whatever you do.
Peak pressure, volumes and liters, and the constant. Or no. And for N, we're just using moles.
N's the number of moles. Yeah.
Okay. And then R is the constant, and then the temperatures in Kelvin. I think I asked all of the questions I needed.
All right, sounds good.
Have a good one.
All right, I'll see you next Wednesday.